Hello everyone, we are Aleksandar Jevtić
and Christoph Reich.
and we are happy to present our ICCV paper Feed-Forward SceneDINO for Unsupervised Semantic Scene Completion. This is joint work with Felix Wimbauer, Oliver Hahn, Christian Rupprecht, Stefan Roth and Daniel Cremers.
DINO is a strong self-supervised image encoder used in various 2D supervised and unsupervised scene understanding tasks. We present SceneDINO, bringing DINO to 3D to facilitate 3D unsupervised scene understanding. At the downstream level, we focus on the task of semantic scene completion, short SSC. Given a single image, the goal of SSC is to recover dense 3D geometry and semantics of a scene. SSC is a comprehensive 3D scene understanding task with broad applications. Most existing approaches for SSC rely on dense 3D geometric and semantic supervision. Obtaining these annotations is very expensive, requires specialized hardware, and is not scalable. Recently, approaches using only 2D supervision have been introduced. Still, obtaining ground truth is expensive, and models trained using 2D supervision exhibit limited generalization. Since large-scale SSC annotations are simply infeasible to obtain, we approach SSC unsupervised. We present SceneDINO. Given just a single input image, SceneDINO predicts a 3D feature field that captures both dense 3D geometry and expressive features of a scene. From this feature field, we can obtain unsupervised SSC predictions. Notably, SceneDINO is fully unsupervised, uses multi-view self-supervision for training, and is feed-forward doing inference. SceneDINO's architecture takes in a single input image, which is processed by a 2D encoder-decoder that produces dense per pixel embeddings E. A lightweight MLP takes in the pixel embedding E alongside a 3D location X and predicts two quantities, a density value sigma and a feature vector F. Finally, the segmentation head H takes in the features F and predicts the semantic P. Training SceneDINO consists of two stages. In the first stage, we use multi-view self-supervision to learn a 3D feature field. In the second stage, we distill and cluster these 3D features to obtain unsupervised SSC predictions. First, I would like to introduce the feature field training. We feed an image into SceneDINO to predict a 3D feature field. Using differentiable volumetric rendering, we can reconstruct images and features from novel viewpoints. For self-supervision, we use multi-view images and extract 2D DINO features. Finally, we train SceneDINO by minimizing a multi-view image and feature reconstruction loss.
After training SceneDINO to predict an expressive 3D feature field, I would now like to introduce our unsupervised segmentation training. Our goal is to learn an unsupervised segmentation head by magnifying semantic feature correspondences and clustering the resulting features. We distill SceneDINO's high-dimensional features into a lower dimensional space, utilizing the similarity of features in the high-dimensional space as a learning signal to enhance semantic feature correspondence. Clustering the distilled feature space yields pseudo-semantic predictions. On a conceptual level, we feed an image into SceneDINO and predict a feature field. We sample features from the feature field for distillation. For this, we propose a sampling approach that picks rich semantic features that capture different semantic concepts by taking advantage of the 3D geometry. Please refer to the paper for more details on this. Alongside the features of the current scene, we obtain KNN features and randomly sample past scenes from a feature buffer, ensuring positive and negative feature correspondences. These features are fed into the segmentation head, reducing the feature dimensionality. The segmentation head is then trained to distill the feature correspondences, using the high-dimensional feature as guidance. Finally, we cluster the distilled feature space using mini-batch k-means. Here, we qualitatively compare SceneDINO's SSC predictions to an unsupervised baseline, namely S4C and Stego. SceneDINO better captures the semantic of the scene, especially for distant regions. SceneDINO provides more accurate segmentations. Quantitatively, we validate SceneDINO's unsupervised SSC accuracy on Kitty 360. We compare against S4C, a recent 2D supervised approach, and our unsupervised baseline S4C with Stego. SceneDINO significantly outperforms our unsupervised baseline in terms of mean IOU. Using DINO v2 target features instead of DINO v1 further improves the SSC accuracy. Overall, SceneDINO leads to state-of-the-art accuracy in unsupervised SSC. We can also linearly probe SceneDINO's feature field using 2D semantic annotations. Compared to the 2D supervised approach, as for C, linear probing outperforms while only training a single linear layer. We also compare SceneDINO features in 2D. In contrast to DINO, our features are high resolution and exhibit better consistency between views. In the paper, we also validate this quantitatively. To conclude, we presented SceneDINO for unsupervised semantic scene completion. We demonstrated the effectiveness of multi-view self-supervision for unsupervised 3D scene understanding. Given just a single image, SceneDINO estimates dense 3D geometry and expressive features. Distilling and clustering the features leads to state-of-the-art accuracy in unsupervised SSC. We showcase strong linear probing and multi-view consistency results. While not in this presentation, we also demonstrate SceneDINO's strong domain generalization in the paper. For more information, please visit our project page. Our code and pre-trained models are publicly available. Thank you.